Hello, my name is Carl, and today I'll be giving a presentation on our paper Feasible and Stressful Trajectory Generation for Mobile Robots. As mobile robots become more pervasive in society, so does our awareness of the potential impact faults in these systems could have in society, not only in autonomous systems that we see every day, but in a wide range of vehicles, from autonomous car crashes to factory robots, airplanes, and autonomous drones, and this list could easily continue. As the impact of these faults becomes more apparent, testing of these systems becomes more important. One way to test these systems is by using end-to-end system testing, in which the system is given a goal, generally some trajectory. The trajectory is then executed in simulation of the real world. The big question becomes how to generate these goal trajectories. Imagine you're a tester given this empty parking lot and you needed to test your vehicle. If you're testing an autonomous car, you could select two random points and generate a typical trajectory between these 2 points. Similarly, if you were testing an autonomous drone, you could take the same approach taking into account the additional spatial dimension. The major problem you would be faced with is that even when only considering traversing between 2 points in space, there are infinitely many ways to traverse between these 2 points. For example, you might follow a straight trajectory between the 2 points, or you might take a curved trajectory between the 2 points. So the first question you might ask yourself is, which trajectories do I want to use as a system test? While trying to solve the first question, you'll realize that many of the trajectories between the 2 points are infeasible. They cannot be physically achieved by your specific vehicle. Thus, for each test, you need to consider your vehicle's physical abilities carefully. Now, one might argue that there are a set of typical trajectories or standard trajectories you expect your robot to do in the real world, and thus want to test. For example, going down a straight corridor. And we agree that exploring these typical trajectories is necessary to validate the behavior of the mobile robot. However, we argue that they may overlook faults that only arise in the presence of stressful trajectories, this thought being analogous to stress testing or load testing software systems. For example, consider the following example of a drone flying down a corridor. Here we're looking at the drone from both behind and a bird's eye view, to get a sense of the drone's environment. We can see that the goal is to fly down the straight corridor, and the drone might pass this test with flying colors. These standard use case tests are necessary to validate the robot. However, were the same drone placed in a corridor with a series of sharp, unexpected turns, you might find faults that arise only under these stressful conditions. Before we talk about what we did, let us formalize the problem. Given a physical space W, and note in this figure we only show 2 dimensions, the physical space could be 3 dimensions as done in our paper. And given a set of waypoints WY inside this space, we also have a robot R that is capable of traversing between a subset of waypoint pairs in a given time step. This subset of waypoint pairs is said to be valid. And a robot R arriving at a given waypoint I will enter with state SI. We want to find a trajectory Traj, which is a set of robot states that are physically feasible and thus only comprise of valid steps. Remember that there's a huge number of possible trajectories, and many of these trajectories are infeasible and thus cannot be realized by the implemented system. We also define a function called score that defines the stress placed on the robot for a given pair of waypoints. This stress could be the maximum deviation from the intended trajectory as shown by the blue line, or any other measurable metric such as maximum acceleration or total time. According to our score function, we want our final trajectories to also be stressful, such that for each feasible trajectory, our stressful trajectories include more stress on robot R. So the goal is feasible yet stressful trajectories. In this talk, I'll go over the conceptual overview that describes the core technical contributions of our approach. The algorithmic solution is presented in more details in our paper. There are 3 main stages to our approach. The first is a technique that allows us to find trajectories. The next stage is a technique that allows us to filter out any physically infeasible trajectories. And finally, the technique to select the most stressful trajectories. To start, let's see how we can go about generating large sets of trajectories between 2 points. First, we populate the physical space with random waypoints. 2 of these waypoints are defined as the start and end positions. These are positions where the robot will start and end during tests. Next, we connect each of the waypoints with edges to form a graph. Finally, we turn this graph into a search problem to find paths through the graph that start at the starting waypoint and eventually end at the ending waypoint. So now we know we could solve finding trajectories by turning this problem into a graph search problem and searching through the graph using the graph search algorithm. This idea is a modification to a robotic planning algorithm called probabilistic roadmap planner, or PRM. Next, we need to find a way to identify the physically feasible trajectories. This is a tricky question. We need to be able to identify whether the robot can physically achieve a trajectory before we execute that said trajectory. The key to solving this problem, or the secret sauce for this problem, was the realization that by incorporating the physical model into the generation process, we could compute how we expect the robot to behave. Let me expand on this. First, we need to know what robot we are working with. In our paper, we're using a quadrotor as shown in the figure, although the following approach applies to any robot. A quadrotor state can be described using this 12th order system, which describes the position in the world, the attitude, which is the roll, pitch, and yaw, velocity, and angular velocity. We know that the quadrotor is controlled by varying the propeller's velocities, which allows it to create forces that ultimately move it. The relationship between the inputs, which in this case were the propeller velocities, and the final position have been mathematically modeled. The mathematical models which describe how these changes occur are called kinematic and dynamic models. Specifically, the kinematic model describes the motion of an object in space, while the dynamic model describes the forces associated with the motions of the object. On the left we show an example of this model, whose input is the rotation of the propellers and the outputs U1 to U4 represent the different forces on the body of the quadrotor. Using these forces we can update the angular velocities, which in turn can be used to update the attitude, which finally can update the velocity and subsequently the position. These kinematic and dynamic models are not uncommon and are used in many fields, including robotics, astrophysics, mechanical engineering, biomechanics, and game physics. Thus, they are widely available for a wide range of robotic vehicles. In summary, using these kinematic and dynamic models allows us to compute the future position of a robot given some input, which in this case is the propeller velocity. If we were to sample all permutations of the propeller velocity and apply them to our kinematic and dynamic models, we could compute all future positions of the robot. The area or volume covered by all future states is called the reachable set. This area or volume is the volume that the robot is physically able to achieve. For example, here we have computed the reachable set of a quadrotor. You can see that after about 1 second, if all motors were turned off, it would fall directly down roughly 10 meters. Also, depending on the combination of propeller speeds, you can see that you would end up anywhere inside this the red dome that's surrounding the quadrotor. If a waypoint was to fall outside this reachable set, we know that it would be physically infeasible for the quadrotor to achieve that waypoint in the given time frame. So we know that using a robot's reachable set, we can remove all infeasible trajectories by only selecting trajectories that lie entirely inside the robot's reachable set. And now the final piece of the puzzle. How do we find the stressful trajectories? Consider the following trajectory. The black line shows the intended trajectory and the red dotted line shows the actual trajectory of the robot after execution. How could we compute the stress on the robot before the robot was to traverse it? Well, to start, let us consider a subset of trajectories. If we can compute the stress on a smaller subset of trajectories, we could apply the same technique to the entire trajectory by stepping through each pair of waypoints. We could measure the stress, which we again demonstrate as the maximum deviation. We know the expected velocity into the waypoint v in, we know the expected velocity out of the trajectory v out, and we know the angle between the two trajectories theta. Thus, all we need is a function f, which in the problem statement we call a score function, that takes in these measurements and predicts the maximum deviation. In our paper, we propose two ways of computing the score function. First, this function could be handcrafted by experts. For example, if an expert knows that high velocities are likely to increase stress, the function would predict that trajectories that have a large v in and v out are likely to lead to deviation. A second approach is that you could learn this function using machine learning techniques if no information about the robot is known prior to testing. So how do we go about learning these functions? We start by generating random feasible trajectories, and then we execute these trajectories and record the resulting stress measures and different features. So for example, here we can see that we recorded both theta and maximum deviation. We also see that as theta increases, so does maximum deviation. When we use machine learning, we can then use machine learning to learn a function that fits the data. In our paper, we use a polynomial regression model where the loss function is the linear least squares function and regularization is given by the L2 norm. Using this new function, more stressful trajectories can be generated. The benefit to this approach is that at no stage do we need input from an expert. You, however, might be worried that they will not perform as well as scoring functions crafted by experts. We compare learned scoring functions to handcrafted scoring functions later in our study. So now we know all the building blocks required for our algorithm to generate both feasible and stressful trajectories. Again, what we described is just a conceptual overview of our design. The paper contains many more algorithmic details and a fully worked example. We've made an implementation of the tool available, with more details available on our website. Here we show two examples which are modified simulations to include walls to emphasize how stressful trajectories could lead to collisions. On the left we see an example of a drone moving down a fairly straight corridor, and on the right we show how very sharp turns could lead to stress which leads to collisions. We evaluate our approach and aimed at answering two main research questions. First, does the introduction of the kinematic and dynamic model improve the ability to generate feasible and valid trajectories? And second, does the introduction of a scoring model improve the ability to generate stressful trajectories? We performed our evaluation in a physical world which was set to a 30-meter wide cube with a volume of 27,000 meters cubed, and placed 250 waypoints inside the world. We ran our study on two quadrotors. The first is called the flight goggles quadrotor, which is a quadrotor simulation made available by MIT, based on the drone in the left image. For this quadrotor, we implemented 4 different software controllers to see if different control methods affected our technique. Secondly, we used the parameterizable quadrotor, which has both a physical and a simulated drone. To answer the first research question, we ran our experiments to see how many physically valid trajectories were generated in a set time as we varied the length of the trajectory. We generated trajectories using 3 different techniques. The first technique used no kinematic and dynamic model, and the results are shown as the blue line with circle markers. The second technique used an approximated kinematic and dynamic model that approximated the reachable set using the quadrotor's maximum velocity. The final technique used a more expensive and accurate full kinematic model. We found that for short trajectories of length 3, it was better to randomly search the graph or search the graph using the approximate kinematic and dynamic model. However, using the full kinematic model started to outperform both other techniques at about trajectories of length 5. In fact, by length 8, both no kinematic and approximate kinematic techniques were unable to generate physically valid trajectories in the given amount of time. We continued our experiments up to trajectories of length 50. And we found that our technique was still able to find physically valid trajectories in the given amount of time. Thus, our takeaway was that using kinematic and dynamic models improves the ability to find physically feasible trajectories. To answer the second research question, we wanted to find out if introducing a scoring model would improve the ability to generate stressful trajectories. To do this, we focused on 4 different scoring models. The first assigned high scores to trajectories with high velocities. The next two, assigned high scores to high velocities with turns of different degrees. And the final was a scoring model which was learned based on the initial set of tests run with no scoring model. To answer RQ2, we generated a test set using no scoring model and used that as a baseline. We then generated 4 new test sets using 4 different scoring models as shown on the x-axis. On the y-axis, we show the maximum deviation of the scoring model divided by the mean maximum deviation with no scoring model. Thus, any value greater than 1 represents an increase in the stress compared to the set of trajectories with no scoring model, while any value less than 1 represents a decrease in stress compared to the set of trajectories with no scoring model. We can see that for both the high velocity and lone scoring models, all trajectories generated had a higher stress than the mean maximum deviation when no scoring model was used. This, however, only shows the results for a single control method of the flight goggles quadrotor. When we look at the results for each of the different software configurations, we found that at least 1 of 3 handcrafting scoring models results in a more stressful test set. More specifically, for both waypoint controllers, including a scoring model that favors trajectories of high velocities resulted in test sets that are 70% and 76% more stressful. For fixed velocity controller, a scoring model that favors 180-degree turns resulted in a test set that is 9% more stressful, with some of the outliers being 40% more stressful. And for a minimum snap controller, a scoring model that favors 90-degree turns induces an on average a 69% more stressful test set. We also show that it is possible to learn scoring models that can generate stressful trajectories for a specific quadrotor that are almost as good as scoring models crafted by experts. Our takeaway from these results was that introducing both handcrafted and learned scoring models into trajectory generations produces tests that on average are 55.9 and 41.3% more stressful than trajectories without a scoring model, respectively. Next, we performed a study using a commercially available quadrotor. To do this study, we ran our experiments on the Anafi drone in both the official simulator Sphinx, which is a modified version of Gazebo, and ran the test in the real world in an empty field. For these tests, we learned scoring functions and showed that in both simulation and real world, our tests on average produce tests that are more stressful than tests generated using no scoring function. From a testing point of view, we know that one might be interested in trajectories that violate certain specifications. For example, a tester might specify that the maximum deviation from the expected trajectory cannot exceed some threshold. In this figure, we show that the percentage of automatically generated tests that violate a given maximum specification on the y-axis and a specified threshold on the x-axis. The results indicate that regardless of the specified maximum deviation, using a scoring model produces a larger percentage of tests that violate the specification. For example, given a specified maximum deviation of 4, that with no scoring model, only 30% of tests generated would violate those constraints. However, the approach using a scoring model would generate a test set with approximately 70% more tests which violate the same specification. Developers can also use these trajectories to investigate further the behaviors which lead to these violations. For example, using the NAFI quadrotor, we plotted the test that produced the largest maximum deviation. Here we show the expected trajectory as the black dotted line, the simulated position as the orange dashed line, and the real position as the solid green line. We found that when flying from waypoints 2 to 3 in simulation, although it did not follow the expected short line trajectory, it flew to only a height of only 29.9 meters, which is inside the test world. In the real world, however, the drone flew to a height of 31.34 meters, which is 1.34 meters over the designated flying altitude of 30 meters. A pilot flying this quadrotor who is not aware of the distinct behavior shown through this trajectory would at best be surprised and at worst experience a collision. In conclusion, we have introduced a novel approach for the automatic generation of feasible and stressful trajectories for mobile robots. The approach was able to generate physically feasible trajectories that caused a mean increase of stress of up to 76%. Thank you.